I'm Mohammad from the Brain team, and I'm going to talk about the particular project with Superstore Noah and Jonathan on end-to-end geometric reasoning. As you may have noticed, we live in a three-dimensional world, and we are surprisingly good at learning object abstractions based on a sparse list of key points that are consistent across multiple views and instances of a particular object category. For example, in this case, different chairs. This can be key point number 1, key point 2, and key point number 3. So one interesting problem is how we can incorporate these key points into our machine learning algorithms, but moreover, how we can automatically discover these key points, very much like humans can do it. So the standard pipeline for incorporating key points starts with annotating a whole bunch of key points and then using a supervised learning paradigm to learn a set of key point detectors, and then using these key points for downstream geometric reasoning tasks. There has been some recent research on using an autoencoder type objective to discover key points automatically. For example, the high-level intuition is that we need key points that allow us to recover a new viewpoint of the object. And then once the key points are learned, again, we use them for some geometric reasoning applications. Now, coming from machine learning, our intuition is that this whole pipeline should be optimized end-to-end. So we should be thinking that different key points are good for different tasks. So whatever task you have in mind, you got to think about optimizing the key points for that task specifically. And so I wouldn't have time to go over all of the details. Maybe go and visit this website and read the paper for more details. But here's the key idea. So think of the following problem. I have two views of an object, and I'd like to estimate the relative pose of the two views. And for simplicity, we only consider rigid objects. Okay, so we know the relative rotation and relative translation during training, but at test time we want to predict those. So we have this neural network that predicts a list of key points. These key points are three-dimensional in our case. What we notice is that we can use a Procrustes problem to recover the rotation, which is not surprising, but we can also differentiate through the SVD to learn everything end-to-end. And that's basically the one example of end-to-end geometric reasoning that I'd like you guys to think about more for maybe other problems. Another useful loss function in our setup is a so-called multi-view consistency loss that has a very simple intuition, which is having the relative rotation and translation, we can project the viewpoints, the key points detected in one viewpoint to the other, and then we can enforce some multi-view consistency across different views. And so when we combine these different loss functions, we get these kinds of key points on ShapeNet categories. For example, the algorithm is able to discover tips of planes and chair legs and relatively intuitive key points. So we have some visualizations as well. Maybe you can look at them yourself on the website. But more importantly, what we realize is that if we use a supervised pipeline, which is we ask annotators to annotate key points based on Pascal 3D on these objects, we get these kinds of errors in relative pose estimation. But our pipeline, without using any key point supervision, is able to lower the relative angular distance between the pairs of test objects. That's it.